Okay. So far, whatever you've done, one of them is this: a current carrying conductor, infinitely long, straight wire carrying current. I've given you all these things, I'm just putting it down. So it's an infinitely long, straight wire carrying current, and if you have a current flowing there at a distance of A, there will be a magnetic field. The magnitude of the magnetic field is mu naught I over 2 pi A. The direction of the magnetic field is given by the right hand grip rule. So the right hand grip rule will tell you the direction of the magnetic field. The magnitude of the magnetic field is given by that equation. Is that okay? So this is for an infinitely long straight wire carrying current. And the other one that you saw was like a coil, a flat circular coil. When you have a flat circular coil of radius r containing n turns, the magnetic field at the center of this flat circular coil is B is equal to mu naught Ni over 2R. Of course, there should be a current flowing through it. The sense of the magnetic field, the direction of the magnetic field is given by the right-hand grip rule. Well, in this case, the right hand, these fingers represent the current, and this represents the magnetic field. In this case, the thumb represents the current, and that represents the magnetic field. So you can see how they are flipped. The same right-hand grip rule. Thumb is current, curved fingers for the magnetic field. Curved fingers for the current, thumb for the magnetic field. Okay, so this is one of them. And then I showed you the solenoid thing. Did I do the solenoid? Mm-hmm. Yeah. If you pass a current I through a solenoid, which has a total length of L and a total number of turns of N, you have D is equal to mu naught Ni. Where N stands for the number of turns per meter, which is number of turns per unit length. N stands for the number of turns, L stands for the length of the solenoid. So if N is smaller and smaller, then magnetic field strength is going to be weaker and weaker also. So the more crowded those wires are, the better the magnetic field. Now look at this. This is also like a solenoid. The wire is, the current is going from here, going through it in one direction, comes out from the other side. So this is basically a solenoid. Look at the number of turns per meter. If you want to find out the number of turns per meter here, what do? You take a definite length, let's say 5 centimeters, and then find out how many turns are there, how many windings are there in those 5 centimeters. So 5 centimeters converted to meters is 0.05, correct? So if I have, in 5 centimeters, if I have 40 of this, so 40 divided by 0.05, which is how much? How much? 800. 800 turns per meter. That means if I take it as 1 full meter, you should be having 800 turns on that. That's just my guess, okay? Now that is basically like a solenoid. So the more crowded they are, the better or the stronger the magnetic field strength is going to be. Alright, so you saw that. And let's move on to the Fleming's left-hand rule itself first. Yes?
Wait, how do you know the direction?
You need to follow this up and see, like the current is going from underneath and coming out from there. So all these are coming out. So this is basically current coming out from there. So you put your fingers like this in such a way that these tips of your fingers are these arrows. Right hand again. Just hold this solenoid like that so that the tip of the fingers are these. And which way is the thumb pointing? That is the direction of the magnetic field. So the magnetic field is along the axis. So this is the magnetic field along the axis of a solenoid. You can write that down. magnetic field along the axis of a solenoid. And this is a magnetic field at the center of a flat circular coil. And suppose there is only one turn, you just have to knock off the end. That's it. If it's only one loop, just use mu naught I over 2R. There's only one loop. And this is for an infinitely straight wire carrying current. The magnetic field next to it is given by mu naught I over 2 pi. So out of these, which is the north pole, which is south pole? Which is north? Yeah, the arrow comes out from the north. And where the arrow ends is supposed to be the south. So magnetic field always like comes out from the north pole and ends up at the south pole. What is a magnetic field line? We drew lines around the earth, remember that? So in this room, which way is the magnetic field? Going from where to where? From there to here, this way. So where is it starting? From the geographic south pole, which is the magnetic north pole. And then from there it starts and then comes, and where it culminates is the geographic north pole, which is the magnetic south pole. Make sense? So what are those lines? What's a line? What's a magnetic field line? Try to recollect what I said about electric field line, then you'll get it. Yeah.
So is that what the path a unit north pole will take?
That's it. How did you define electric field? Electric field electric field needed a positive and negative charge, right? Electric field, this is called a dipole, a positive charge and a negative charge. Now, if you take a unit positive charge and release it here, which way will it move? It will just run away this way. If you release a unit positive charge here, where will it go? Straight into it. If you release a unit positive charge somewhere here, what will happen to it? This will push that unit positive charge and that will pull it, and so it will go like that. If I release it here, it will go like this. Now these lines are called the field lines, electric field lines. These are called the electric field lines. Alright, so around a dipole you have electric field lines. It's pretty much the same way. So what are these field lines? They are imaginary paths taken by a unit positive charge when placed in the field. Now for magnetism, it's a similar definition. But you need, so suppose you have a magnet here, north, south. What you need to bring here is a unit north pole. Can a unit north pole exist?
No,
Can a unit north pole exist? No. Even for a miniature magnet, which is an atom, there's a front and a back. So in electricity, you can have a positive charge totally isolated and you have a negative charge totally isolated, it's possible. But in magnetism, the magnetic dipole, they always come together. So if you have a magnet, there's a north, there's a south. South has to be there. So how do you imagine a unit north pole? A unit north pole you can imagine if the magnet itself is very long. It's a long magnet, so the north is here, south is very far away. Makes sense? A simple example of plotting these magnetic field lines. How do you get a magnetic field lines presence felt or experimented? You need a magnet. Take this magnet and put it in your bathtub. So that's a bathtub from above. How do you make a magnet stay on top of the water? Like you need water. You need water in the bathtub and you need to make a magnet float. How do you make a magnet float? Or how do you hold it then? Yeah. Tell me.
Could like put a stand and hold it
You
up.
can actually put a stand from the bottom of the tank, right? From the tub. You put a stand, a plastic stand or something like that, and the magnet stays there on the top. That's one way. Or you can also put a styrofoam kind of a tray and put the magnet there on top and then somehow reinforce the styrofoam tray. Okay? So this is a magnet sitting on top of the water. Now all I need is a unit north pole. Even if it is not a unit pole, at least can you get a north pole alone? What you need to do is take a steel wire, or a steel, thin rod. Just take a thin steel rod and magnetize it the way I did it. Just magnetize the rod or wire. So once you magnetize the steel wire or steel rod, you have you have a long wire like that, long steel wire. You magnetize the whole thing. Where's the North Pole? Right there. Where's the South Pole? Right here. And then what you do is you take this needle, or take this steel wire, poke it into a piece of cork, and let it float in the water. Make sense? Just let it float in the water. Now from the side view, it will look like this. From the side view, it will look like from the side view. Okay. From the side view, this is a magnet, and you put the cork, make it float, and that's the needle. You get it? The steel wire is like, so the cork is actually making it float, and this is the acting as a North Pole. Where's the South Pole? Too far away. You're trying to make the South Pole too far away, so you can just ignore it. It's not going to make a big influence. At least here, which is going to dominate? This North Pole or this South Pole? It's a North Pole. So we can simulate that effect of unit North Pole just like this. Now when I release this cork over here, what will happen? Now think more practically into the tub. You're not doing it right now, but so if I release this cork over here, it'll just keep going straight. If I release it here, it gets attracted. If I release it here, it'll get pushed out from here like this. But the more and more it's getting pushed out, this south is going to pull it back. So it'll turn around. So this is what you'll notice. This cork will actually float in the water, and finally, slowly, it will come around and go back. The imaginary path taken by a unit North Pole when released in the field. That is a magnetic field line. So this is a magnetic field line. That way. Now if you release it there, it will just get lost. There's no strength to bring it back again yourself. So this is how we drew the magnetic fields around the Earth as well, the same idea. So magnetic field lines are imaginary lines starting from the North Pole and ending at the South Pole. And that is kind of representing the path taken by a unit North Pole when released in the field. Make sense? Okay? So this is the North Pole and that's the South Pole. So the magnetic field is going to be inside the magnetic field is in that direction. But from here it comes out and here it goes in. So if you try to track the magnetic field lines around it, it will be like this. You go around like that. So just imagine it's a magnet. So if I take this and make a current pass through here and take it out from here. If I make a current go here and let the current come out from here, that's an electromagnet. This is one of them will act as a North Pole, one will act as a South Pole. Now if I keep a solid iron inside, that solid iron will be magnetized. because you are imposing a magnetic field on the solid iron or steel or whatever. And because I'm imposing that direction for a long time, it will get magnetized.
Can we do that?
We can, but this is not meant to be used as a solenoid. A solenoid will not have any resistance. It will be mostly made of copper. This is meant to have a resistance. This is called a rheostat. It's called a rheostat. It's meant to have a resistance. So this is a variable resistance. And this one's job is not for magnetic field. Its main job is to change the resistance in a circuit, so thereby you can control the current. Okay, that's not really yes, it is a solenoid, but the main function, because of the high resistance, pushing the current in it also will have limits. But if it is solid, just copper winding, it will have better strength of field, unlike this. Yeah, if you take a solenoid which is made of copper, and if you pass electricity to it, it becomes a magnet. So even if I keep this outside, or if I keep this outside, it will get sucked in. If I release it from here, it will just go in. But it can't come out, it will get trapped in between. Because if it has to come out, it needs the velocity and all that, momentum. But even if it has momentum, when it is going here, the magnetism is actually, like magnetic field is actually pulling it back into itself. It's not easy to let it escape. Well, if you can momentarily turn the magnetic field on, you can make it go like a bullet. Sort of. Yeah, so if you momentarily turn it on, what will happen is this will accelerate and gain velocity, and then you turn off the magnetic field. So it will just go with that velocity, it won't stop. Yeah.
When it's in the magnetic field, would it like not touch the
Sides?
So yeah, would it be up like levitating kind of?
No, it will be along the greatest magnetic field here, right in the middle.
So it'd be right in the middle.
Touching, because gravity is another factor you can't. Gravity is also there, so it will also sag down, touch the bottom. Okay, so I'll try to show you that. So this is a rheostat. The main purpose of this rheostat is to control the current flowing in this. So the total resistance from here to here is, it says here, 89 ohms. But then if I connect a wire from here to here, I'm just including a fixed resistance of 89 ohms. Instead, if I'm going to connect it between here, or between here and here. Okay, if I connect between those two, look what's happening. The current goes from one, it goes through the coil. When it comes here, it gets picked up, and then it comes out from there. You get it? So right now, if I keep it right in the middle, the resistance is probably around 45 ohms. If I take it all the way to this end, see which way the current is flowing. The current goes all the way, comes all the way, and then gets picked up. So it's fully 89 ohms. If I bring it here, it is 0, because the current comes here, it gets picked up. So this is kind of more of a variable resistor. So I don't want to overload this, because this says it cannot take more than 5 amperes, say. But this one is safe. The safe current over here is only 2.2. But I don't want to give this current straight away to this, because this is copper wire and this is a solenoid. You can see that this is a solenoid. It goes from one side to the other side. I don't know which way it is. We'll see. So if I pass a current, from, let's say, the positive terminal to here. So if I have a current going from positive to here, then the negative one, I want to disconnect it to the negative terminal. This negative one, I'm going to clip it to this. and from here I want to return it back to the negative. Doesn't matter what color wire you're using, it's all right. All right. The only thing is we should make sure that they're not touching each other and no talking. All right, so I wired it up. I'm keeping right here in the middle, so therefore the resistance is locked. So even if it is 6 volts that's coming out from here, because of this 49 ohms and all that, it's not going to create much of a current. It will create some current. And you can see, is it magnetized right now? Nothing at all, right? But if I turn it on, nothing at all, or nothing much. I'm going to reduce the current, reduce the resistance, so it increases the current. If this trips, that means I'm exceeding limits. All right. Not much. Don't see it happening. You go closer. I can feel it. I can feel the magnetism. You can just try it and see.
I want to see it. Could we get like something a little lighter?
Oh yeah, I feel
Do you
it.
feel it? If you can feel it.
Yeah, do you have something like stick to
Now I'm going to make it like 0 resistance momentarily, because I don't want. All right. Now you can see this.
Oh.
It feels like this screwdriver.
See that? Yeah.
Wow.
So I just left it here, and then it's going.
So like,
It's a magnetism.
if we use something smaller like this screwdriver, will it spin in the middle? Hold on. Like something with less mass.
Yeah, it will be better, I think. But then it's coming back. You see, it's trapped inside.
Puff out the front.
Or I can do that probably by cutting this off immediately as I release it.
Hey Kyle, get out of the way.
No,
Hey
do it
Ethan,
go.
get out of the way.
Nope. It's tough. That's why you need some better methods of doing it.
It worked, kind of.
Yeah,
Hit rain.
it is.
Hit rain. We don't settle all the time. Could say that.
Yeah, it came out this time. Yeah, it all depends on the timing. So if you can actually make some method of detecting where it is and then releasing this off, it works. And you can see this very clearly that's magnetized. So as soon as you turn it on. So what is happening is, but the problem is this is DC. And so it's got just one pole. If I release it from here, it should go the other way. Yeah, it's going from here to there. All right, got it. Okay. So basically what I did was I put a rheostat in case, but then I put 0 resistance in the rheostat. I don't want this rheostat coming the way. Now, so what is the rheostat's main job? To control the resistance. So in this case, we can wire it like this to control the resistance. But a similar thing is what we call as the potentiometer, and I think I've discussed that. Haven't I discussed the potentiometer?
Yes, that's what I got confused with.
That is a potentiometer. Like suppose I put 12 volts here. If I put 12 volts there, the two extreme terminals are these two. The two extreme terminals are those two. And this is supposed to be the center tap, like this. So if I have a center tap like that, how many volts do you think will be here? Approximately 6 volts, right? If I drag it like this upward, it'll be 12. If I drag it all the way down, so this is more of a potential divider. This is a gadget that actually can divide the potential and give you what you need. Now, you can actually think of it as part of an amplifier. Now what is getting connected here is a preamplifier. Preamplifier is a circuit that is doing the first part of the magnification of the signal. And what goes in is the microphone. So the microphone is the input, and the preamplifier will amplify it to some extent. And then it pushes here. Now this is supposed to go to the main amplifier. And the output from here goes to the speakers from the main amplifier. So whatever signal is coming out from the preamplifier, if I connect this all the way up here, the amplifier will get all of the signal, and therefore it will be loud. And if I drag it downward here, what's happening? When I drag this down, what is the signal coming to the amplifier? Nothing, and therefore it will be 0. So basically it's like a volume control. You control things with this. Just a potentiometer like this will be able to do all the controls. In fact, if you have seen volume controls or graphic equalizer, you know, most graphic equalizers are like this. Like you slide things.
Oh, yeah.
Yeah, this is big, massive, but then you're looking at semiconductor type of things. You're looking at semiconductor type of things, and then when you slide it, it changes the resistance, and accordingly the whole behavior changes. So potentiometer, now where is potentiometer used in practical sites? Some examples? Volume control, yeah. The volume control knob itself is a potentiometer. Well, can it act as a rheostat? Can it act as this one? Well, it is not designed for that. Normally a potentiometer will have a very high resistance, like in kilo ohms. The rheostat normally will have ohms, because here your job is to control the current, not completely block the current off, right? Now the potentiometers are not always going to be made up of these wires. You can have carbon ribbon. You can have a carbon ribbon and get the same potentiometer action. This is just a part of the yoke. You see this? Throttle, mixture, props. What is inside here? Potentiometers. You can see that. You can see 3 mounted potentiometers with 3 terminals. So when you're doing that, you are rotating it. And when you rotate, what is happening is instead of you sliding it like this, it's basically doing a rotational thing. So how come carbon film do this change of resistance? Come over here. All right, I can get closer. You can't see it. You can't see it.
Oh, alright.
Get closer. I'm just trying to put this multimeter right there so you can see it on screen. You can? Yes. Now can you see this thing over here?
Yep.
What is this? Just graphite.
Graphite.
I'm putting a coating of graphite on paper. Now obviously it's a very thin coating and therefore it will have very high resistance. But graphite is a conductor. Now this is supposed to be, I'm going to use this as a resistance meter. So I'm going to put it on 200 kilo ohms. That means it will read in kilo ohms. See what I'm doing over here. I'm going to touch one side here and one side there and tell me what's the reading. What's the reading? 32 point something. Watch what I'm doing here. I'm just going to scoot it this way. Now what happens?
Lower.
Is the resistance changing?
Yes.
It's getting lower.
Now
Lower.
lower. So basically, this is a variable resistance. See, that's a variable resistance, and that's exactly what is done on the potentiometer that I showed you. Instead of being straight, it is like an arc. So you just basically touch like that. Make sense? All right, go back. All right. Oh, it's magnetized already. See, because you put it inside for some time, it's already magnetized. So yeah, it is very useful actually, because when you are trying to put in a screw somewhere deep, this will be very useful, just to get it magnetized. Or if the screw falls off and it is pretty difficult to reach it, this is the best way to go and pick it up. So that's why most screwdrivers actually have a steel tip which can be magnetized. All right, now coming back to solenoid, B is equal to mu naught Ni. So what is a potentiometer? It's basically a potential divider. A potentiometer is a potential divider. You can use it for multiple purposes. All the controls in all the simulators and all the controls are potentiometers. Lots of them. Okay. All right. So we saw this. Now, force on a conductor carrying current. I think I already drew the picture for it. So if I have a magnetic field like that, if I have a magnetic field going from left to right, now between these two is almost pretty much uniform magnetic field. It's uniform magnetic field everywhere. Say it again? I was just testing you all. All right. So we have magnetic field going from left and right to right hand side. Well, this is just a two-dimensional thing, so you try to understand it that way. Now, magnetic fields are going to be uniform if nothing else is in between. But if I have a wire in between, if I have a wire going into the board and carrying a current into the board, so the current is going into the board, this current has its own magnetic field. This current already has its own magnetic field around it. And what will happen then is these magnetic fields from the magnet will get distorted because of this. So the magnetic field of the magnet will go like this, and no lines will intersect. Magnetic field lines or electric field lines will never intersect. So this is what happens. The field lines will actually kind of squeeze itself like that. And at the bottom, it tries to run away because it's opposing. So overall what you see is there is a distortion in the magnetic field that was created by this magnet because of the magnetic field of the wire. Yeah.
Doesn't it go from south to north? North to south.
Oh, from North Pole to South Pole. I'm not showing the entire magnet. Magnet is here. This is one magnet, that's the pole of the other magnet. Right? It's like two magnets. Like I'm keeping the south pole of one here, north pole like that. So it's like two magnets, but I want the field in between. There are different kinds of magnets. There are some magnets like a horseshoe, like that. So north is here, south is here. Okay. So what happens is, you can see the magnetic field lines are getting crowded over here and very less dense over here. So the magnetic field strength is pretty high in this area, and because of the crowding of lines, this wire will be subjected to a force because of the extra crowding, and the force will be downward. The force is going to be downward, and that's what we call as the force on a conductor carrying current in a magnetic field. Force on a conductor carrying current. Force on a conductor carrying current placed in a magnetic field. Force on a current carrying conductor carrying current placed in a magnetic field. This is pretty much the same. So you are applying a magnetic field that way, and the current is going into the board, and it experiences a force downward. And this is basically Fleming's left-hand rule. Again, call it by the right name and pick up your right hand, proper hand, not right hand. Call it by the correct name and pick up the correct hand. Okay, this is Fleming's left-hand rule. Now, the other rule we saw was right-hand grip rule. This is Fleming's left-hand rule. In this chapter, we won't do right-hand rule at all. So this is Fleming's left-hand rule only. And what are these fingers representing? FBI. Force, magnetic field, current. Or you can also say father, mother, and I. Father for force, mother for magnetic field, and I. Okay, whatever be the convention, take it like this and keep your fingers always perpendicular to each other, and then you can find out. Now, how do you do this? A very common mistake from students is this. It's all a matter of direction, this way or that way. But when you're using this one, you will be given two of these, and you want to find the direction of the third one, right? If two of them are known, the third one can be found out. So what you need to do is this. Which way is the current? Current is going in. Is that right? Current is going in. And then you have to switch the magnetic field to this side. So what students normally do is, they just, magnetic field that way. When you do that, you already change this one also. So what you need to do is, you fix one first, hold it there, and then twist the other one into the right spot. You get it now? You don't have to really hold it, but understand that you're doing it. So fix one, and then turn it all the way, and you'll see the thumb pointing downwards. That's how we detect which way the force is. It's a simple rule. You just have to apply it right. Okay? So Fleming's left-hand rule, try to understand and try to use it the right way. Now I'm giving another example. Here, this is a wire carrying current, and the current is going upward. And the magnetic field is from that door to that door. So which way is the force? Current is going upward, magnetic field going that way. Which way is the force? Yeah. Good. Check it out and see. It's a simple thing. So current is going upward, magnetic field is going that way, so twist it, and then the force. Now it's easier for you to twist on the book because you can twist the book around. But in real situations, you're not going to this is the situation, that's it. So you need to use it right. So there is a current flowing in a wire, and there's a magnetic field in that place, and therefore it will experience a force. Like for example, in this room, the Earth's magnetic field is going this way, right? So if I have this wire carrying a current, like this, the current is going from here to there, what will happen to this wire? Magnetic field is going from there to here. Magnetic field is from that place to here. You saw that direction, right, last time? So magnetic field is starting from there and going this way. And I'm holding the wire here, current is going from here to there. So which way will this move? So magnetic field is going that way, and the current is going that way. So this will sag. You get it? This will be sagging downward because of that extra force. Now if I flip the current direction this way, magnetic field still stays the same, then this will experience force upward. So this thing, instead of sagging, it will go like that. Now why it won't be that noticeable in this room with the Earth's magnetic field? Because Earth's magnetic field is very weak. Earth's magnetic field is like in the order of 10 power minus 4 minus 5 and all. So it is not too strong. But if I keep a strong magnet and do this, you will see the force acting on it. You can actually feel the force present. I could have shown that. Should I?
Yes.
A thin wire, it would sense better. It would show better. Okay, I'm going to make it loose, really loose.
Just kind of neutral. Looks like it's kind of moving.
Yeah.
You
Seems
see
like-
when he pulls it away.
Seems like it is.
Ooh. Yeah, it seems like. Yeah.
Oh, that one. it was the other magnetism. There is an action, but it's not very clean seen because this one is too thick. You need a very thin string, basically a metallic string. This one is thinner. No, it's not connected. All right. Now let's go back. I'll see if I can fix it for you. With a okay. Now, Fleming's left-hand rule only tells you, yes, there is a force, but that force depends on what factors. Now, to investigate that, we have to set up an experimental, experimental kind of a platform. So for that, first thing, you need magnetic field. How do you create a magnetic field? If you want to create a magnetic field somewhere, a solenoid will be the best thing. So here is a solenoid to create a magnetic field. Now, I need to pass a current through the solenoid so that it will produce a magnetic field. I'm going to get a magnetic field right in the middle like this. This is the direction of the magnetic field I'm intending to get. All right? And that magnetic field depends on what? Mu naught N I. I'm going to call it I prime because this is not the main current we are talking about. So this current, how do you get this current? We need a rheostat. We need a power supply, just like that. And there it is. So this will make sure that there is a current flowing here. And you can have a switch so that you can turn it on and off. So this is a solenoid. Now what is going to be in the middle of the solenoid are two railings. You know what is railing, right? Railings. And those two railings are going into the solenoid like that. So it's going inside. And I'm just drawing the diagram for it. Those are two rails. Can you imagine that? Three-dimensionally? The two rails are horizontal to each other. And how do you hold the rails? By using a plastic strip which is pivoted. So the rails are held by a plastic, but of course it's not going to stand like this, it's going to fall off, right? So what you need to do is make it like a balance. So you have to have something on this side of a similar length, something on that side with a similar length, and here you can put a pan and put some weights on it. So this is the experimental setup, and where is our conductor to be investigated on? Here is a conductor that's to be investigated on. That's the conductor we are talking about. And the conductor is placed on the rails like this. It's not just placed, but it is like firmly fixed. Like that. You get it? So these are conductors till here. These are also conductors, but there's no contact. So it's more like a balance. Right now, with all turned off, this is not connected, nothing is connected. Try to get it balanced. How do you get it balanced? Put some weights on this side and get it balanced, right? So once it's balanced, we now need to turn this magnetic field on in that direction. And I'm going to send a current through it as well. So this current that I'm going to send is like that. That's rheostat once again, so that it will control the current. And this current is going through this into here. And it will go like this and come out from here. I mean, it will go on the rod that way. And it will come out from here. And I'll grab it and I'll take it from here. So what you see is there are two currents. One to create magnetism, and the other one to send that current to the conductor. Now, if the magnetic field is in that direction and the current is going inside, which way will it experience a force? Fleming's left hand rule. Left hand rule. Left hand. Many of you are picking your right hand for some reason. Fleming's left hand rule. Okay. Again, that's a very common mistake from student side. You just pick up whatever hand is available and then make it wrong. Fleming's left hand rule. Apply the Fleming's left hand rule. Tell me which way the conductor will experience a force. Down. So this conductor is going to experience a force downward. This conductor is going to experience a force downward. According to Fleming's left hand rule, current is in, magnetic field is that way, force is downward. So what will happen? This balance will be offset, right? How do you bring it back to balance? Add some mass over here. And if these arm lengths are exactly the same, think of principle of moments, you done? If the arm lengths are exactly the same, isn't the weight mg supposed to be equal to this force? So by measuring mg, you are measuring the force on a conductor carrying current placed in a magnetic field. Make sense? Now, how do you investigate the force? Just by measuring the mass or the weight. You measure the weight and you get the force. Change the current here. If you change this current, that means this current gets affected and the force will be lesser. Make sense? So you can experiment it with all the variables possible. Let's say this. Force is seen to be directly proportional to the current I. So that means if the current is 0, there is no force. If the current is more and more, there is more force. So graphically, it's going to be a straight line representing force and current. Other variables, this magnetic field. If you change this magnetic field, how do you change this magnetic field? Changing this current, right? If you increase this current, magnetic field is going to increase. If you decrease this current, magnetic field is going to decrease. And what is seen then is that the force is directly proportional to the strength of the magnetic field as well. If the magnetic field is not applied at all, it won't experience any force, even though there's a current flowing in it. Because it's only the interaction between the two fields that actually makes it happen. So B is proportional to I, F is proportional to I, and F is proportional to B. And then the other factor is the length of the conductor, which is from here to here. You can space the railings like that, right? Now have more length. So if you space this railing, separate the railings like this, you can have more length of the conductor involved. And if you do that, so this is B, F is proportional to B, also a straight line. F is also seen proportional to the length of the conductor. That's also a straight line. Then the other factor is the angle. And the angle is right there. This is the angle. Right now I put it at 90 degrees. But it need not be 90 degrees always, right? So that is the angle. So in other words, if I'm having a conductor sitting on the railings like this, it's 90 degrees. What if it is sitting like this? Come on. What if it's sitting like this? It's not 90 degrees now. So an angle is involved. So when you have an angle involvement, if the angle is 0, there won't be any force. If the angle is 90, it gets a maximum force. So F is proportional also to sine theta. F is proportional to sine theta. And sine theta goes from 0 to 1. So F is proportional to that. So the angle is an important thing as well. Combining everything together, we have, combining all this together, we have F proportional to B, I, L, sine theta. All factors are there. and F is equal to K BIL sine theta. And K is equal to 1. And therefore the formula becomes F is equal to BIL sine theta. And that's the equation that you have seen. BIL sine theta. So if you want to determine the magnitude of the force acting on the conductor carrying current in the magnetic field, that's the equation that you need. You need the magnetic field, you need the current, you need the length, you need the angle. Now if it is maximum force you're looking for, then angle is 90 degrees. Any questions? No questions? That's weird. Any questions? You should be having questions, otherwise you're not following things.
Why is K1?
Why is K1? Nobody's asking that. I just wrote K is equal to 1 and then you said, okay, so be it. No, you should ask that. Why? Don't let anybody just, like derive something and say, oh, this is equal to 1, okay, therefore. No, you're big enough to understand that there is a K that is constant of proportionality and it has to take a value, but there is a reason why that is 1, K is equal to 1. I won't tell you right now. As we go on to the next chapter, I will tell you why K is 1, because you will automatically see it. Okay? We will prove K is equal to 1 in the next chapter, but right now take it as that, BIL sine theta. Now it's the same formula that's going to be applied for a charge moving. Watch this. If a current is going that way, and the magnetic field is going into the board, which way is the force on the conductor? Current is going that way, magnetic field is in.
How's it going with
Current is going that way, magnetic field is in, so the force is going to be that way. And now this force is on so many electrons on the conductor, moving which way? Electrons are moving in this direction. And you know the drift speed, V. If you bring in the drift speed with the current, you should be able to derive this expression, F is equal to BQ V sine theta. That is an equation that we will get to derive. Substitute I as, I equal to NAEV, that equation. Substitute all those things, you should be able to derive this.